Hi and welcome back to the minimal CPU system. I've designed this little machine entirely from TTL logic to be as enjoyable and educational as I possibly can. It's made to explore the basic principles of computers, and I've built a lot of revisions over the last year. Despite being deliberately simple, this CPU is on the other hand powerful enough to never stop being usable. It can run some serious software. If you are new here, I suggest to check out my other videos on this channel where I explain things in more detail. In the first part of today's video, I'll present two general ideas any DIY computer could significantly benefit from. That's memory banking and expansion ports. These ideas are neither my own nor are they new. In fact, they belong to the alphabet of CPU design for decades, but I think it's handy to see them implemented in a minimalistic way. In part 2 of this video, I'll showcase and release the final revision of my minimal CPU system that benefits from those ideas. Even though a while ago I thought I was done with my CPU design, these two ideas just had to be part of it. Software-wise, there's also a lot going on right now, but that's for another video. DIY CPUs usually have a quite limited address space shared by RAM and ROM. My CPU, for example, features a 16-bit address register reaching 64 kilobytes of memory. I'm using 32K of flash and 32K of RAM. For a larger address space, the number of connections quickly explodes, usually enforcing higher circuit integration, which is contradicting the point of a minimalistic CPU design, so there's a kind of a sweet spot here. I'm using these flash ICs here that cost only a little more than $1 and provide 512 kilobytes on a 19-bit wide parallel address bus. But since our CPU so far can only make use of 32K, the upper four address lines, A15 to A18, need to be tied to ground, rendering 480 of the 512 kilobytes useless. That's got to be changed. What if we control the upper address lines with this 4-bit 74HC173 ledge or register instead? We only need to come up with a way for our CPU to control this. There are basically two approaches. We could memory map a specific RAM address to this register. We would need to build a circuit that detects whenever our CPU writes to that address and then copy the bus value over to the bank register. A leaner way could be to use a free control line of our CPU's control word to build a dedicated instruction that moves a value into the bank register. From software perspective, LDI bank number loads a bank number into the A register of the CPU. With the first approach, STA bank address moves the content of A into the bank register by memory mapping it to a bank address, whereas with the second approach, an instruction bank moves A into the bank register. Both approaches have their pros and cons. For my own CPU, I have decided to use the second way. Of course, there is usually no such thing as a free control line, but hey, working around that is part of the fun. The implementation in hardware is straightforward. The bank-in control line enables the input of the latch. The microcode of the bank instruction simultaneously puts the content of A onto the bus. We simply connect the lower four bus lines to the inputs D0 to D3 and are done. The outputs Q0 to Q3 are always on and connect to the high address lines of the flash IC. So now we have 16 software selectable 32K banks available. That is a lot of non-volatile memory for a DIY CPU. Let us take a closer look now at the expansion port idea. An expansion port provides an interface to connect arbitrary peripherals to a computer. To give you an idea, that could be a counter, a game controller, timers, an SD card or audio output, a blinking lights panel, a DIY video adapter, an I/O card, a keyboard interface or even Ethernet. Really anything you can come up with. I am especially grateful to Nisse Kohlberg, aka Slow Corners from Sweden, for many fruitful discussions here. The expansion port is in fact his contribution, and as he puts it, it is transforming the minimal CPU into a minimal CPU system. So thank you for being part of this, Nisse. Let me anthropomorphize for a second and ask, how can a CPU talk to an expansion without knowing its inner workings? Simple answer, the CPU doesn't have to. All it does is talking to a specific memory location. The expansion card automatically hijacks and maps these accesses to its functionality. How can that be done? Well, let's jump into the schematic and have a look. Starting on this overview, let's zoom into the memory section and double click on it. At the top, we see the 16-bit memory address register. Below we see the RAM, the flash IC, and we already know the bank register. Read and write access is controlled by the control lines RAM in and RAM out we see here. But they only have an effect if the chip is enabled. And this is where it gets interesting. The active load chip enable signals are generated by the two NAND gates up here. Let's zoom in. NAND gates are only low if both inputs are high. So let's work our way through this logic. First we have this inhibit signal here. It is tied high with a 4.7K resistor. So for now let's assume it's high. In that case you see that the highest address line, M15, determines the state of the chip enables. If M15 is high, which is the case for addresses hex 8000 and above, the RAM gets active. If M15 is low, the flash IC is enabled instead. Now take a look at the expansion port pinout. It makes the memory address and control lines and also the system bus available to the outside. But what about this inhibit signal? If an expansion card pulled it low against the resistor, this would inhibit both flash and RAM access. So by decoding the memory address lines M0 to M15, an expansion card can inhibit normal RAM access and insert its own functionality if a specific memory location is being accessed by the CPU. Address decoding sounds more complicated than it is and usually involves just a few TTL chips. But let's leave that to the next video where I plan to build a simple I/O card. Before we jump to the showcasing, there is just one more thing. I've managed to double the clock speed of the CPU, but I will spare you with the details here. It's now running comfortably at 3.6864 MHz, executing approximately 0.5 mega instructions per second. That's about the processing power of a C64 or Apple II. Now on to some showcasing of this new and hopefully final release of my minimal CPU system to whet your appetite for building it yourself. First off, it's free. I'm again releasing it into the public for all CPU enthusiasts out there enjoying learning and diving into this stuff as much as I do. I mean, I'll certainly not object if you want to give something back and support this channel and what I'm doing. If you feel that's something for you, there is a link in the description. Before showcasing the latest features, let me briefly point you to a link where you can hang out and meet other minimal enthusiasts and get help or advice. Just go to minimalcpusystem.boards.net. There is a software and hardware section and also a complete documentation to get you started. Speaking of documentation, let's click on it and take a look at the Minimal's user manual and reference I've written to get you started step by step. It covers pretty much everything you need to know to get the most out of this CPU. Leave me a comment if you find something odd or missing. The link is in the description. Now let's power up the CPU and see the bank switching in action. We start out on bank 0, where I have stored my demo programs. Type M to bring up a menu. We can use L to load stuff, T to show the table of content, and the N command to switch to another bank. Let's load and play Pong for starters. Okay, let's hit reset and type N1 enter to select bank 1 now. It also contains a lot of files. But bank 4 seems to be free. Let's save a part of the RAM to the SSD now. All the other banks are empty. Finally, here's a close-up of the expansion port, but more on that in a later video, where I'll build a small memory mapped I/O card and switch on some LEDs. By using these Arduino-style connectors here, expansions are stackable, so you can in principle combine a game controller interface with an audio output. And there is more to come in the near future. As I said, I've teamed up with Nisse Kullberg, aka Slow Corners. Nisse is a senior software developer from Sweden. He has already implemented a 4th programming environment on the minimal CPU. He has published it in the Minimal Boards software section. But that's probably for another video and is not my own work. The project repository, to which I'll also link, contains the complete build information, schematics, Gerber files, bill of materials, ROM images and demos. And this is it for today. Thanks again for watching, subscribing and supporting this channel. It has been an amazing year for me and I'm really grateful and humbled by the many friendly comments I have received from you guys. Take care. Bye.